All right, it's about 10 o'clock here, and it's time to start our September version of the engineering webinar. This is sponsored by the ABA Engineering Academy, and we're really happy to announce today that the Georgia and South Carolina Broadcast Association has actually joined with us to help promote these monthly webinars. And we have with us, going to have a co-host now, and John George is with us. John, you with us today?
I am right here, and good morning to everyone from all three states.
All right, we appreciate you joining us, John, and John will be with us every month and help co-host our webinars. We have a very exciting lineup of guests today. Two gentlemen who are at the top of their particular systems that they operate with. So we're going to get right to them. Let me ask everybody, if they will, to show that our program will run a little bit as smooth as possible, and also to help with bandwidth, that you, if you're an attendee, make sure that you mute your video and mute your audio. That way it won't have any interruptions. If you'd like to ask a question of any of our participants, there's a chat box down at the bottom or either at the top of your screen, depending on which operating system you're using. You can just click on the little chat box and it will open up and you can type a question, and our presenters will actually, well, they'll answer it, or either they'll try to find out or they'll make something up, I suppose, if they don't know the right answer. Well, let's jump right into our first presenter today. When we talk about audio over IP and the conversation gets turned around to that particular subject, one name always pops up, and that's Jay Tyler with Wheatstone Corporation. Jay has been with Wheatstone for a big number of years now. I guess 20 or 25 years or so he's been with it. And Jay is probably ranked up more frequent flyer miles of anybody I know, not only across the United States, but around the world, in going and talking about their product and audio over IP and the different things that go along with it. So Jay, I'm going to turn the program over to you now and just share some words of wisdom with us.
I will, and thank you, Larry and John George, and everybody from for being here today. I'm going to take some time today to discuss what, for me, for you folks, is going to be our third generation of audio in education. Over the years, I started working with a lot of you on analog stuff. And then when it came, another, say, 10 years into the 2000s, especially you, Larry, we built that beautiful facility down in Montgomery using those D4000s and a router, and that was all AES. And that was a good 10 or I guess a decade working with you folks, trying to get you guys educated on sample rates and digital audio and different wiring schemes, and get you guys off of the 66 blocks to the Krone blocks. And as you said, this is my 24th year at Wheatstone, and I find myself having the pleasure to work with all you guys again on the IP audio stuff. And, since 2006, Wheatstone has jumped into the IP audio world, and we've seen a lot of advancements in AOIP. We've seen a lot of strategic partnerships. We've also seen a common transport mechanism evolve. And one of the first things that was out there with the folks that, back in the amusement park days in the 90s, we knew CobraNet. And this was a way amusement parks and malls were distributing audio. Telos jumped into it early on in the 2000s with their protocol Livewire. We got a lot of positive response from the industry about let's do things over AOIP. Some of it made sense. We were a purist audio company. The transport mechanism of AOIP was questionable, but the benefits of the interaction with the automation system and communicating with third-party hardware really outweighed any disadvantages of moving stuff over Ethernet. We got to the common connector. And so here we find ourselves at a juncture point where customers had choices. When we went from analog, we all used analog consoles. So everything was analog, pick your console of choice. When things went AES, You know, you looked at manufacturers, whether you're going with a standalone system or you're going to do a distributed routing system like the early on Klotz, the early on Logitech, the way SAS is built, you know, and then we jumped into this whole thing. And it was a process, and I guess an education working with everybody on the advancements. And so in the last 10 years, you know, some names that have been popular: Wheatnet IP, Axial Livewire, and Ravenna, which is a German flavor of our AOIP. Ultimately, folks, all of our AOIP stuff is very, very, very similar. And if you were to look at the actual packet structure of the different manufacturers I just mentioned, 95% of it would be the same. What makes all of these protocols different is clocking. And you can say that Wheatnet is a protocol or Livewire is a protocol. It's not. What that is, it's a clocking scheme. It's a way that Wheatstone gets these metronomes from this clock signal via metronome from this box to this box to this box, keeping everything timed and aligned and phase lock looped. So now we're at a juncture point where we have this thing called AES 67 and it's interoperability. I'm going to educate you on just enough that you need to know that what you're working with today, whether it's the Wheatstone stuff or the Livewire stuff or the Dante stuff, all of us manufacturers are working hard to make it easy for you folks to plug stuff in and out, just like you used to in the AES domain when you had an XLR. We want to bring that same thing to you folks with the AOIP world. And so we're going to discuss some interoperability. But I know you folks have been on all these calls and all these meetings for the last 7 or 8 months. And as Larry mentioned, I traditionally have been on the road 200 days a year. And because of COVID, we haven't been traveling a lot. And so I'm going to take about, I don't know, say about 5 minutes out of this presentation and take a break from technology a little bit and talk about Wheatstone Corporation, show you a quick video. We're going to pop into my processing lab, and then we're going to back out and we're going to talk about this device right here, which is our new Blade 4. And Blade 4 is our key to interoperability in and out of everybody else's system. So let me start with a quick little video right here, or I'm sorry, a PowerPoint presentation, and we'll just keep going. So let me just share this, and we'll run this. So one of the things I don't know if everybody on this in the meeting knows is we're a U.S. manufacturer. We make everything in-house as much as possible at Wheatstone. We don't buy third-party power supplies. We design our own power supplies. We like to have control over the product. And Wheatstone was founded back in the 70s on this premise that we were going to do as much stuff as we can. And what you're looking at on this slide is our facility. It's about 52,000 square feet. At our peak, we house about 100 employees daily. And the people that work at Wheatstone, Larry, you mentioned I was here, 24 years. I'm still a newbie at Wheatstone. I think we have 15 people at this office that have been here for over 35 years. And the founder of our company, Mr. Snow, has done a great job in retaining his workforce. And so what you have now is you've got a team of people like that with hundreds of man years of experience. And so I think it makes us a little bit different that we are building the products, doing everything we can in-house because we still believe in that broadcast quality. When people start talking about IT or you mention IP, the first thing you hear is, oh, we use off-the-shelf products. Well, in broadcast, we've never used off-the-shelf products. Off-the-shelf products generally does not possess the redundancy or that level of comfort broadcasters get from buying from a specialized manufacturer. And some of the things that we do is not because it's less expensive for Wheatstone to make stuff, but it gives us control over the product, over the components we use, the testing of everything. And so it makes us a more agile private company here. Even though we're buying resistors, capacitors from all over the world, everything's assembled here at Wheatstone. And what I've shown here on this slide is our Wheatstone assembly floor at night. I'm sure I crawled up on some shelving I wasn't supposed to, and I took this photo. But it's a big facility, and we do a lot of different things here. And so some of these videos that I'm going to show you, there's pictures, and here's one of our 4 surface mount machines. We don't make the raw card in-house, but we do all the mounting of components. So we actually design the raw circuit card in a program called Mentor Graphics. We know where all the DSPs and FPGAs need to go. And what we're doing here, let me turn that down a little bit. What we're doing here is we're actually pasting. We turn gold into silver. And what we're doing is those are gold pads there. And what we're doing is we're putting a paste down for this machine to pick and test every single resistor capacitor before it mounts it. And then it places it on these cards. And these cards that we're looking at now are anywhere between 6 and 7 layers. Once you place all the components on a card, you got to put it in a pizza oven. And what we're looking at here is basically it's one of our big ovens that heats up everything to about 290 degrees Celsius. So all the parts have been technically burned in and tested before it ever is touched or powered up by a human. We've got a big 5,000 square foot metal shop. So it doesn't matter if it's stainless steel, aluminum, acrylic, wood, plastic. We cut it, we mill it, we shape it in-house, and we even do our own powder coat. Again, this isn't because Wheatstone's saving a lot of money on manufacture. You look around, there's millions and millions of dollars in tooling here. But what it gives us is ultimately quality control. Here's one of our Cincinnati lasers here, just cutting out blank things. You know, it takes a lot of guys to run this equipment. We send our guys to school, just like you guys have continued education on the broadcast stuff we're doing. Our team of experts continually goes out to schools for manufacturing. Screen printing, here's a meter bridge. So some development that we've got going on here at the office. Here's a closer look at our Blade 4 product that we have right now that's being in development. This is going to be sort of the key for us going forward as far as interoperability goes. This is how a console starts. You know, we cut a frame, we screw some end caps on it, we place the motherboard in. Everything is tested and listen tested by a human when it leaves here. So, like again, one of the reasons we do all of our in-house manufacturing, there's not a lot of volume in broadcast, gentlemen and ladies out there. It's pretty much a low volume, I'm going to say high profit item, but it takes a lot for development. And one of the things that we're seeing now is we are done with the TDM stuff pretty much. Everything, even our television stuff, is moving over to IP. And what we have pictured here is one of our new Strata television consoles in the forefront. And in the background there, you'll see a couple more that are getting ready to come out. So even during COVID, we've stayed pretty busy. I'm about to show you a video now, and then I'm going to move into another room and show you our processing lab. So just take a couple of minutes and watch this while I'm out of the way. All right, you should be able to. All right, there was a little video of our little town of New Bern, North Carolina, and just wanted to show you one other thing here that we're working on at Wheatstone, and that is our processing lab. I'm just going to sort of move the camera around here. You'll see we have a lot of the guys, various processors. It's all built on WeakNet IP. Here we've got our cool little processing RF, analyzer rack here that we've built. Over here is sort of central master control. And I'm just going to pop over here. And what we have here is the ability to switch different formats. And you can't see these, but we've got pretty much every processor ever made here. All the Orbans, all the Omnias, and all our different boxes to sort of give, I guess, an objective starting point for all of our processing stuff. So now that I'm done with that, I'm going to go back to my camera here. Cool. All right. So back here at the processing lab, and now what I want to talk to you guys about a little bit is Nielsen. One of the things that we're doing with our processors that we can now talk about is we're actually moving the encoder into the processor. So Nielsen's given us some code recently, and our engineers are working on getting that code in the Aurora processor. So we're going to do all the watermarking and all that stuff actually in the box now, opposed to externally with all those encoders. And I think we're getting really, really, really close to having that complete. So that is something to look for as far as the major markets go, is having those encoders built into your audio processors, saving you guys a lot of rack space, air conditioning, and a few other things. So with that said, I'm going to plug in my headset, and we're going to talk about some AOIP, Blade 4, and interoperability. I don't see any questions yet, so probably because I've been talking and showing off the factory. If you do have any questions, the chat box is open here to the right. I forgot my audio in. All right, we're gonna go back to share screen for a second. And I'm gonna go to the next slides. Skip that. Just popping through a few studios here. I know you guys aren't getting out either. Here's a few of the builds we've done recently out there. I wish I could go visit these. Some sexy studios. Right here is Bonneville that was built actually during COVID. If you get Radio World, there's a great article in there this week about that. All right, so talking about AOIP, AES-67, and interoperability between manufacturers. Earlier, I mentioned WeakNet IP, I mentioned Livewire, Ravenna. There's also Dante. Well, in the beginning, back in the early 2000s, we all did our own clocking scheme. So if you wanted an AOIP system, you basically had to go all in with one manufacturer. Well, the early stuff, the WeakNet IP and the Axios stuff, we all used 250 microsecond packets. And the reason we did that is because of live audio and latency. And by sending a lot of packets at a very fast rate, it allowed us to keep all of our stuff synchronized. Well, about 10 years ago, a lot of other manufacturers wanted to jump on the AOIP bandwagon. It's very expensive, it's very time consuming. So there was committees that were formed, and one of the first early pioneers was the AES 192 committee. And what these guys did is they basically set a group of recommended standards how AOIP should be implemented on an open platform. So some of the things that changed early on for all of us manufacturers was multi-channel support. We've been doing mono and stereo in radio forever, but the TV guys got on board. So now that your AOIP systems have to support 8 channels, because we're doing 1 or 2 for radio or microphones or stereo, but when we get into multi-channel, so we had to
up the count. And so one of the big things about Blade 4 is it supports all those different formats. The next thing is flexible packet time support. The biggest thing we had to deal with 15 or 20 years ago was AES synchronization. You know, early AES systems had master clocks. We dealt with 32, 44.1, and 48. We still have sample rates that we deal with in AOIP, but the most important thing that you're going to deal with is packet time. You can't listen to a 125 microsecond packet if your system's running at 1 millisecond. And what we found out is the majority of the PC motherboard type ancillary gear, that's going to be the Comrack, the new Comrack stack multi-unit, the Telos VX, Dante. These guys all use 1 millisecond packets. So, which is 4 times slower than native WheatNet IP moves around. So to play well with others, we had to actually increase our packet time. So Blade 4 now does 125 microseconds. We do 250 microseconds, which is our native. We support 1 millisecond and 5 millisecond packets. So if you folks are out there and you're thinking, oh, I got a new VX, I want to plug into WheatNet, we'd have to add a Blade 4 to that because the VX does not spit out natively 250 microsecond packets. But if you have an Axia node, you can take an Axia node, plug that into the same switch as your WheatNet IP, and those two systems will talk back and forth at 250 microseconds, no problem. Something that you'll need, and I guess it's a gray area right now, is who's going to be the master clock. In the early days, early sound cards, you'd have to sync them to an AES reference or a word clock. What we're doing now is to stamp every single packet and know when packets leave a system and when packets arrive. We've got to support PTP clocking. And some of the products out there will do that now. SONEFFECT makes a nice big master clock that you can put in your facility and use it to sync everything together. The X node will do a handful of devices on it, so it can actually be a master clock. Blade 4 as well, it can do a master clock. But you're going to need something to keep time because we're stamping every single one of these packets. Something else that we threw in Blade 4 for you, and this was, I'm sure Charlie Wooten out there has done some of these links, but a lot of guys want to use Motorola's, they want to use Ubiquiti, and all these different types of radios these days. And early on, if you didn't have a full duplex system, and it was a little bit of a distance, there was no way you were going to use nodes or blades on a not a full duplex system because we're sending these packets back and forth at such a high rate, and the radios couldn't switch fast enough to handle it. So we all discovered that, yeah, you want to have full duplex radios all the time. Even that case, sometimes, whether it was a marginal network or it was a shoddy line of sight, sometimes these devices wouldn't work. And this is even the same on somebody's private fiber network. If you had any jitter or you had multiple things on a network, our early AOIP devices were sensitive to that. So one of the things that we built into Blade 4 was 170 milliseconds of buffering. So if you've got to go building to building or you've got a marginal hop, we can actually dial in a buffer setting and we can hold those packets and send them in big blocks to traverse, less than perfect networks. So, and this also will help us interface with all the other guys' stuff out there. Here's the really nuts and bolts and where this AES 67 has driven Wheatstone as a manufacturer. And like I said, everybody else is pretty much on board with these. In the past, all these systems were multicast. We would spew everything everywhere all the time. The private networks, you got tons of bandwidth. You only got a few hundred sources and whatever, so you're never going to even touch the bandwidth on your network. But now when you want to jump outside of your facility, and I want to go from New Bern to Charlotte, or I want to go from New Bern to Greenville, then you might, and you have a limited amount of bandwidth, now we support unicast. And what we're doing is just sending one stream out at a time. So The Blade 4, we couldn't do it in the older stuff, but we can now. And if you have a Wheatstone system and you're interested in some of the interoperability I was talking about, all you have to do is buy a Blade 4. Once you introduce Blade 4 to the system, that guy can do all of this new interoperability for you. We support both 44.1 and 48 sample rates. It's a mixed bag here in the United States, who runs what, where. 44.1 was the HD default standard. Half the guys do that, half of them do 48K. This is important when you're intermingling these systems. Everything outside the US is 48K. Packet timings here that I listed, the three popular ones, the 1 millisecond, the 125 microseconds, that's more TV. PTP profiles, guys, this PTP is gonna be, this is the clock. And the 1588 was the default standard, the IEEE that's on there. And then we also have AES 67. We do transport, packet spacing. Down below, you see the jitter buffer. And what that is that allows us then to dial, to tell this receiver, hey, I want you to wait 100 milliseconds to grab a bunch of packets. This is a transmission link. We really don't care about delay. We want a good quality signal going through there. And then after that, we support the 2110. This is really what the TV guys got on board with the 2110. This is going to be the reference for all of their stuff going forward. And everything that Wheatstone's designing, I'm going to tell you in the future, is two things, is all for AES 67 and 2110 interoperability. And the second is cloud-based stuff. So our StreamBlade product, our processing we're working on, even this stuff, our console stuff, we're using a new tool set called Qt for development. And eventually, you know, we see a lot of this stuff wanting to go into a cloud. I don't know if it's going to be Amazon's cloud, SAS, or your personal server, but one of the parallel paths that Wheatstone's doing is not only assuring interoperability between everybody's stuff, is the fact that this stuff can move. It doesn't have to live in our hardware. And that's sort of another topic. You know, I get a lot of the groups saying, Jay, we want to put things in the cloud, put things in the cloud. Right now, Wheatstone's a corporation that it's software. Everything we're doing is software, but our software runs on our hardware. So it makes support very, very easy. So from the engineering guys, yeah, it's great to have something somewhere else that you don't have to maintain, you don't have to plug in, you don't have to rack or air condition, but it's also a control issue. And so, you know, when we think of do or die, and, you know, we're the main support for the world for media, information, and news, just don't be so quick to jump on everything into the cloud. There's certain things in the cloud that will work, but you're still going to have, you know, audio monitoring microphones at a radio facility. You're going to need to get those around, and you're also going to need to work with different manufacturers. So going forward, AES 67 sort of levels the playing field for all of us transport companies. So people aren't caring anymore. Is it a LiveWire network? Is it a Ravenna network? Is it a WheatNet network? And for somebody who makes really cool boxes, I think it actually, this whole interoperability thing empowers Wheatstone, because now it's not so much what's on the cable going back and forth. I've got this signal, now it's going to hit this box. What am I going to do with it in the box? And that's where I think, you know, the Blade 4 is sort of advanced in that area. We also do NMOS. This is going to be discovery. If any of you guys have ever, if any of you have ever worked with interoperability now or early Axios systems, very manual process. Okay, I've got a source from Wheatstone. Here's its multicast address, 239, blah, blah, blah. And you got to put that in, type that into a receiver. Now, NMOS is going to be the discovery for all this stuff. So people will make these programs, and you plug a Dante and a SAS and a WheatNet and an Axia together. You'll actually see the streams and the source names. So it'll make sense for you users. And again, a lot of this is to make the user experience a lot easier on the other end. So things like the discovery here and the packet timing and translation. So that's pretty much it on our AOIP stuff that we've got coming out on Blade 4. A couple things that I didn't talk about, the hardware side of Blade 4, redundant network links, redundant power supplies for the TV guys that love it. And another really cool feature about Blade 4 is we've got a couple codecs in there. And these codecs are meant to talk from Montgomery, Alabama to Birmingham. So I've got two WheatNet systems, one on each end. I don't want to go use a Tie-Line or a Comrex. Because we put more horsepower in this, we've got a couple codecs that will actually support Opus and some AAC algorithms. So, you know, we'll be shipping this thing pretty soon. It doesn't leave any WheatNet guys out there abandoned. It's just going to be another box you're going to plug into your system to enhance your user experience. So that's pretty much it. Any questions?
Thank you, Jay. I had one quick question you might address is how do you see the switching over to audio IP generally throughout the country? Are people abandoning analog and what percentages do you see?
Okay. So we make about 1,000 consoles a year, have for, I don't know, last 20 years. And about 25% of those consoles that Wheatstone makes, and that's Wheatstone and Audio Arts together, are analog consoles. We still sell a lot of mid and small market consoles. You know, from a guy who makes digital consoles, if more than 50% of your sources are analog, buy an analog console. You know, early on, Larry, when we were building, in John George, we did the university down there in South Carolina. Remember the D75s you bought? We had a lot of analog cards in that thing. And remember, when you got a digital console, when I want to bring a mic in, a CD player, a telephone line, or I want to get a set of headphones or speakers, I'm doing A to D and D to A conversion everywhere. So if you've got a small talk station in Mississippi, you got 4 microphones, you got an analog sound card in your PC, you got an analog hybrid, buy an analog console. And if you have to have that AES output or that IP output, but buy another box. So I keep telling people there's still nothing wrong with analog. It's just the ability to do snapshots, recall, and, you know, send, whether it's AES, Larry, or AOIP, anywhere around the facility, you know, which is almost impervious to noise and signal loss. The transport part of the whole digital thing wins every time. But nothing wrong with analog consoles. A lot of time, and gosh, sometimes you can put them now. They all got the RJ connector on them. We all conform to Studio Hub. And in one of our Audio Arts boards, we actually give you a digital output. So you can have a digital output to interface with something else. On a popular note, and you're going to see this in all the boards, guys, and even on our mic processor, USB audio, it's wonderful. It really is. It's easy. The drivers are discoverable. You know, there's no logic. So for you guys that have like Adobe Audition machines, your internet computers, you don't need to mess around with audio drivers and spend money with us or Axia. Use a USB. So if you're using, you know, any of our AOIP systems, or even like these little Audio Arts boards, if you don't need a start-stop or you don't need a control, guys, USB audio works great, and we're starting to put them on everything. So that's just something else to add to the mix.
Okay, thank you very much, Jay. That was quite a bit of information. We are recording this, and it'll be up on our ABA Engineering Academy YouTube site later this afternoon. So if you need to go back and review some of the stuff that Jay covered, it will be up on there. Thank you very much, Jay.
Thank you,
And John, turning it over to you now.
All right, thank you. We're going to introduce our next guest, Sean Edwards, who's Director of RF Engineering for Shively Corporation, or Shively Labs. Sean started his career in RF in 1984 with the U.S. Navy, and interesting operated, maintained, and repaired weapon systems aboard aircraft carriers. I guess Sean, you didn't make any mistakes or you wouldn't be here today. After he returned to Maine, he worked as a lineman, line sweep technician, and cable television, building, aligning, and maintaining thousands of miles of transmission and dozens of satellite downlink stations across the Northeast region. He joined up with Shively Labs in 1997 as a senior RF field technician. Then in 2009, moved into the test and development arena and assisted in product development. In 2012, Sean became the RF designer and project lead for Shively Engineering. During this time, he's built a handful of new FM antennas and several new filters. And it's if you ever get a chance, just like if you're in Eastern North Carolina, go to Wheatstone. If you get up into Maine, you want to stop in and go to Shively Labs because it's quite a fascinating place. So Sean, it's all yours.
Well, thank you. Thank you for that introduction, John. As you can see here in Maine, we've already started the winter season. That's a picture window out the back door here. Not quite yet. We're getting there. It was pretty cold this morning. So I just wanted to thank everybody for attending. And this is it's actually my first Zoom presentation. So bear with me if I stumble a little bit connecting the screen share and whatnot. But today we're going to be talking about combiners, FM combining, where you have a situation where you're going to be taking two signals either at the same, whether they're two separate transmitters combining into an antenna, or if you're looking at a larger system where there's 3, 4, 5, or on up to 20 stations, where you would have to have a very complex balance combining system. So there's some simple configurations and much more complex configurations. And we'll talk a little bit about the kind of what kind of details you need to look at in order to get the most bang for your buck. So rather than a 4-pole filter with cross coupling you can put any station within 800 kilohertz next to it and it's always going to work. That's one of the more expensive options, but it may not be what you need. You may be able to have a simpler or some different configuration which will allow you to achieve the ends of isolating the two or more transmitters from each other to keep spurious generations from happening, and cost. So I'm just gonna, let's see if I can figure this sharing screen out. And right here. Okay, so we're going to talk a little bit, when you might need a filter, what your requirements are. Bandpass filtering versus notch filtering. There's situations where notch filters can produce a better result, depending on whether you're looking at a compromise between isolation and maybe you're looking at VSWR performance or group delay asymmetry might be a concern for you. Also looking at, like, if you're going to a new site and you have your antenna is going to be tucked right up underneath, let's say you're a translator and you're going into a new site and you're going to be tucked right up underneath a Class C station. Well, you need to know how much isolation you're going to have there in order to size the filtering so that you know how many poles to use and how much attenuation you need for that situation. So there's alternatives to the more traditional approaches where you, like I said before, you're throwing a 4-pole filter in a situation where you really might only need a 2 or 3-pole filter. So every time you add a pole to a filter, it increases the costs. And as the power level requirements go up for filtering, the cost increase. So if you can really get an understanding of the site conditions that you'll be operating in, that's when having that discussion with the manufacturer, that's when you're going to be able to come up with some creative and cost-saving designs. So, you might need a filter if you've been affected by repack. That's sort of winding down now, but that's still happening. You may have been granted a CP for a translator for your AM station. Somebody might be moving in to a site that you're already at that may require filtering on your system. At that point, it's last in, so that work out the details on that. But no matter who's providing the equipment, there may be a situation where you have a need for filtering where you didn't prior to that. Or you might be, might have an opportunity to move into a consolidated multi-station system, and that might be what's going on. So also there's always the inevitable where there's some damage to the tower or storm damage or whatnot, and you have to find a suitable alternative for a transmission site. And in those situations, quite often filtering is needed. So what's, your requirements? You need to have at least, I can't even see this on my screen. That's one of the things here going on. Okay. You might have part of this cut off on your screen, but basically it's just Title 47, subsection 73.317, where, and subsection D of that, where it's talking about anything removed from the carrier of 600 kilohertz must be attenuated by at least 43 dB, 43 plus 10 log power in watts. So that's going to be that much below the unmodulated carriers, or 80 dB, whichever is the lesser of the two. And ultimately, it's whether you're meeting the spec or not. If there's a audible or a degradation to the signal, it still would need to be addressed. So you might even meet specs sometimes or just be on that borderline. And if there's any complaint or any interaction that's measurable, then that would have to be, you'd have to enhance that isolation. It doesn't require as much isolation, but it would have to be enhanced to remove that problem. And again, if you're last in, how that rule works. If you're last in, you've got to make it right. So ultimately, we're talking about transmitter input isolation, and you need greater than 40 dB. 40 dB is the absolute minimum, and that's at that point your transmitters are not generating spurs, or the spurs are below the acceptable level. So we shoot for 46 to 50 dB to ensure compliance. And you can achieve this attenuation through a number of different ways, a combination of different things. Antenna isolation being one. The filter attenuation will add to that. And transmitter turnaround, there's a little bit of turnaround loss in a transmitter. It can be as little as 6 dB, and older, probably none of the transmitters in operation today would be that poor, but in analog tube transmitters, 13 dB was a number that was used quite often and still is a pretty good estimate of what kind of turnaround loss. With solid state amplifiers, that can be as much as 20 to 25 dB. It depends on the manufacturer. But that's one of the functions, one of the parts of the puzzle that can get you where you need to be. So where does the 40 dB of attenuation occur on a filter? Well, if you're talking about bandpass filter, there's a transmission. I probably ought to start the slideshow. This, again, new at this. So I kind of like this, but I'm going to do this so that everybody can see. So if you look at the curves here, a two-cavity resonator has some attenuation on the skirt, but 40 dB doesn't occur until you're 8 megahertz away from the bandpass frequency. In a three-pole filter, that point where the green trace here is representing a three-pole filter is going to, that point of 40 dB is going to occur a little sooner because the skirt's a little bit steeper at around 2 megahertz. So if there's two stations combining that are 2 megahertz or further apart, then a three-pole filter are closer together, then you would have to have cross-coupling in those three-pole filters. But if they're further apart than 2 megahertz, then just a standard three-pole filter will suffice. And then if you want spacing closer at 1.4, then 4-pole. So depending on how far apart the two or multiple frequencies are, that is one of the criteria for selecting how many poles of filters you need. And so in bandpass filters, those are the rules of thumb. In notch filters, that might be a solution. They're not widely used. Bandpass filters are being widely used because they not only take care of the problems at the time of the design, they're kind of future-proof. They're isolating further out in the band and beyond, where notch filters are just going to attenuate the offending frequency. So you can, if you use notches, you can do a couple of different sets of notches and notch out 2 different frequencies and produce a lot of attenuation at those 2 frequencies, and pass with very little insertion loss the frequency that you're interested in passing. So in this situation, it's 94.3 megahertz, and it's 1/4 of a dB of attenuation. And you've got a requirement in this example for just 400 kilohertz below the frequency. 400 kilohertz spacing is it gets difficult because there's distortion within the band pass of your pass frequency. The closer the notches get, or the closer the resonance of the band pass filters get, the more there's interaction between the two. So here's an example of a bandpass filter with notches at plus or minus 400 kilohertz, but that bringing those notches in that close to the bandpass, again, it affects this bandpass region. So you have frequency roll off, your frequency response is affected, the group delay is affected, and the insertion loss is 1.73 dB. Rather than 1/4 of a dB with notch filters. So in low power applications, we see a lot of requests for notch filtering. And this is an example of the matching that can be achieved with notch filters. It's not very good. It's an example of showing how it's when you're looking to notch out a frequency very close to the bandpass, this is one of those results that you just can't, without reducing the notch value, you cannot improve the VSWR. So that's one of the trade-offs there. And this is the bandpass of the VSWR response of the bandpass solution there. Again, here's the group delay distortion. So on one side of the bandpass, the distortion is around 200 nanoseconds, and on the other side, it's around minus 25 nanoseconds, so a delta of about 235, 240 nanoseconds, which isn't too bad when you look at what distortions start to become noticeable in the audio, which is around 350 nanoseconds. Where in the bandpass, the group delay is as much as a microsecond. It's, let's see, it's almost a microsecond. It's 800 nanoseconds here. So different filters give you, in different approaches, bandpass or notch can give you different results. So let's say you have a antenna system that's right on top of each other. You're not going to get any isolation there, essentially. They're right on top of each other. There's no vertical separation, and there's no chance for the signal to attenuate before it couples into the other antenna. And here's an example of 2 antenna systems where they're not collinear, but they're right on top of each other. And since these are 8-element log periodics, the pattern's fairly narrow. And so you can expect a little bit more isolation in this situation, but it's still going to be fairly strong. It's going to be probably between 30 and 40 dB away from each other. And if you're looking at your antenna or where your antenna may be going in an existing system, that vertical separation becomes very important. And I'm just going to move along here a little quick. I wanted to get right to this, so I'm skipping that. So how much isolation do you have? If you're sharing a tower and you've got vertically separated antennas, you know, this is a good estimate of what the isolation would be. So using this formula, you're looking at the antenna to antenna isolation, and if you, so there's a red trace, a yellow trace. Red trace is a calculated half-wave dipole. Yellow is measured value from our model 6810 antenna, and the blue, the measured value from the 6813 antenna. And then again, I'm going to move this. There we go. That's calculated directly from the formula as the green trace. So, and then I just, because I didn't separate it more than 6 lambda, I just interpolated the trend line here to show what it would be beyond that 6 lambda separation. So again, this is vertical separation. So you can see that at 1 lambda, you've got about, I'm moving things around here so I can see. At 1 lambda, you've got about 30 dB. At 2 lambda, you're getting into, for all the examples except for the 6813. Now 6813 is a type 1 radiator and it has some downward radiation characteristics. So that's why that one is not as much isolation as the remainder of these examples. But at 2 lambda or 20 feet, you've got about 40 dB of isolation. So just in the antennas, you got 40 dB. So if you're 6 lambda, you know, 70, 80, 100 feet apart, if you're 100 feet apart, you're going to be around 70 dB down. You can almost do without filtering. So that's really an important part of figuring out what you need for filtering. If you're horizontally separated, using a different form of that formula, you're taking into account the gain of the 2 antennas if they're sharing the same aperture, and the side lobe, the gain of the antenna and the side lobe value if you're in the side lobes. So if you've got horizontally separated antennas that also have a vertical separation, you can make estimates of what that isolation would be. So in this chart, you're seeing that, again, the bottom axis is lambda and separation, and the y-axis being the amount of isolation between the 2 antennas. And here, so horizontally separated, you're out all the way out to 10 lambda, yet you only have about 37 dB of isolation. So you've got to get about a mile away before you're down at 70 dB. And in those situations, filtering becomes really important because the isolation value doesn't drop off as quickly. And that's, so when you're in an antenna farm, filtering, everybody's got to filter because there's so much RF around. I'm just going to give a couple of examples here. An example of 2 frequencies in the same antenna. So there's no isolation in the antenna. It's the same antenna. It's a shared antenna. So it's a branch combiner, and they're separated by 2 megahertz. The filters provide at about 46 dB of attenuation, and the transmitter provides about 6 to 20 dB, depending on what it is. So the result is going to be 80 dB of attenuation to any of the spur frequencies. No problem. The filters give you what you need, even though the antenna is the same antenna. If you look at 2 stations 2 megahertz apart on separate antennas, separated by 2 megahertz, the antenna would provide about 30 dB of isolation. The filter is going to provide about 40 dB of attenuation, and the transmitter is going to provide between 6 and 20, depending on what type of transmitter it is. So again, it's greater than 80 dB for of attenuation to the spur frequency. Now, if they're only 1 megahertz apart, now here's a situation where, I mean, this is not an uncommon situation to be combining 2 frequencies that are megahertz apart or 800 kilohertz apart. The antenna, again, is only going to give you about 30 dB of isolation between the antennas. The filters will provide 20 dB of attenuation at 1 megahertz, and the transmitter is going to provide between 6 and 20. So the result might be greater than 80 dB, but you might only have 76 dB of attenuation between them. So in that situation, you would need cross-coupling. So we would be enhancing the isolation of this being 2 3-pole filters with a common output. And each of those pieces of coax on the top are the feedback loop, where we take part of the energy from the first resonator and reintroduce it to the third resonator at an odd phase angle, and it causes a phase cancellation, and by that a transmission zero or attenuation or a notch. So if you look at how you'd go from the 20 dB in that example to greater than 60. Here's the transmission characteristics of the first station, and the result of the cross-coupling gives you a nice deep notch here of attenuation. Normally, without it, it's symmetrical to the other side. So it's called, the skirts are symmetrical. And in this situation, we've introduced the cross-coupling. So we have a notch at the other frequency. And this is the other station, and a notch at that first frequency. So when you're looking at the input to input isolation, it's greater than 65 dB. So in this situation, 3-pole filters with cross-coupling was the answer into the same antenna, and it's greater than 60 dB in one direction. And so you've got the attenuation at the fundamentals, but you also have this attenuation at the spur frequencies out here on the way back out from anything that's generated in the transmitter at 65 dB down is attenuated yet again, another 60 dB or so at the spur frequency itself. We're running a little short on time. I'm probably going to be buzzing through here a little bit, but so if you're combining, now we're talking about 2 high-powered stations, or a high-powered station, you want to combine a lower-powered station with it. You can do that, but there's a few things to consider. There's a few caveats. The transmission line, the output coupling of the output coupling structure of the low-power station needs to meet the voltage handling requirements of its input and the high-powered station. And so through electromagnetic simulation, we can simulate those conditions at this junction where this is the filter here, this main showing the fields and the different intensities of that field. Notice in the corners, there's hardly any field, and centered, what you can't see here is there's a probe here. Centered around that probe, the field gets more and more intense. So this is the energy coupled out of the filter into a piece of transmission line. This is simulation of the output of the antenna port, and this is a line going to the second filter. So looking at that junction, we can under the power conditions that would be present at 40 kilowatts applied in this example, this is a 3-inch to 1 5/8 junction. So if you, and I integrate the voltage along the line here so that it can calculate what the RF voltage is. And in this situation, it's 1337 volts. Well, 7/8 line only tests to 5800 volts DC. And when you use this formula to calculate the RF voltage, it's beyond the limit. You know, it's right at the limit there. So that's not acceptable. You know, anything that changes in the system can cause that to fail there and arc over. So then you increase the line size to 1 5/8, same 40,000 kilowatts applied, and the voltage is the same, but it's over a longer distance, and your RF test limit of that line is almost twice what voltage is present. So that's got a good safety margin there. And then of course, 3-inch to 3-inch, it'll certainly handle the voltages. So here's an example of how you might do it. There's a 24-inch cavity and a 16-inch cavity here. And this one's running 20 some odd thousand watts. And this one is only running around 8. So in this situation, we use 3-inch outputs, 3-inch line, and we do a lot of this combining, and we do those analytics to ensure that the lower power station is going to work in those considerations. But that's a big cost saving. If you don't have to have two 24-inch cavities, why use them? So we're getting close here, so I'm going to wind up. But here's another example of some of the things that we use to pair up filters and branch combiners. This is a little spreadsheet I put together. So you put in the power level, the frequency, and it spits out what will be the best solution for 40 dB of isolation and for the power that's going to be present. So through using those tools, we can put together configurations like this, where you've got two 24-pole filters. One of them has cross coupling here. This is a 12-inch cavity with cross coupling, and in order to get all these frequencies to work properly together, we had to use one balanced combiner, but we could use smaller cavities. So here's an example of a cost-saving design that's gonna, that the details have been looked at, and the system is designed specifically for what's required with the proper safety margins in mind. And again, this analysis is done through simulation, and this is representing the balance combiner, and this the 3-station branch combiner. Here's the common out for the branch combiner, and here's where it feeds into the output hybrid of the balance combiner, and right here. So these 3 stations combined right here, that feeds into the output wideband input to the balance combiner module, or an M+3 in this situation. So, and there's the responses. Here's the responses from the branch combiners and from the balance combiner. You get a nice flat response by the action from the hybrid. And the transmission characteristics. So you got 3 stations packed right in here, and they're all isolated from each other. And here's one, this is just a way off to the other end of the band there. And here's the isolation measurement. So here's the 40 dB requirement, and all of those stations, port to port, all of the combinations are all better than 40 dB. So there'll be no spurs generated in that system. And here's the measured values, 45, 50, and then that one's the one that's out on the end. And here's, so these are the different ports to ports. As you can see, this is 10, 20, 30, 40 dB here. So this is an interaction region where there isn't any power. These are the carriers down here measured at 63 and 83. And this one at 54 and 100. So there's another section, but we've run out of time, and I'll take any questions you might have at this point.
All right, thank you, Sean. I think all this points out a very important thing is that if you're planning on doing any kind of combining, whether it's full power stations or even translators, a lot of people now are combining translators into one antenna. You just really need to do your homework and have a company like yours there to do all the calculations, because they appear they can be sort of complicated at times.
At times, yeah. At times you can, and that's one of the things that we try to do is work and get as much information about the site specific information, and that is really key to designing the most efficient combiner.
Sure. All right. Well, thank you very much for that presentation. That was a lot of information, and we, as we told you earlier, it's actually. It is going to be recorded. It's recorded, and we'll put it up on the ABA Engineering website. John, you have any final comments?
No, I don't. I will mention for a number of those engineers that also assist their management teams that the 25th is the deadline for the FCC regulatory fees. And you want to be sure that you don't miss that deadline. So if you work with your owner or manager dealing with issues like this, you might want to remind them to be sure they are aware of it. And again, thanks to Sean and Jay both for participating today. They were both great presentations.
All right, our next engineering webinar will be on Tuesday, October the 20th. And we actually have scheduled for that one Frank Foti from Telos, and he will be with us for that one on October 20th. So make sure you put that on your calendar and join us in. Thank you, everybody. Our presenters, Jay Tyler and Sean Edwards, and John, appreciate your input as well. And we'll see you next month.